The other day on my way to work, I was thinking about the idea of why we teach chemistry, or what's the big picture. And so I made up some ideas and I banged my face against them repeatedly, and I came up with this pseudo lesson. And this isn't like straight content like the other videos. This is more of a, why does stuff happen and how's it going to end up, and how does chemistry give us the power to figure that out? So I want to start a few steps back with like scientists in general. And if you were to go up to somebody and say, hey, you know, what does a scientist do, or what's the purpose of a scientist? I think the intuitive and reasonable explanation is that scientists explain stuff, right? We pay them to figure out stuff that we can't figure out, and then we pay them again to digest it and explain it back to us. And that goes along with how we picture scientists as like these people in labs, wearing a lab coat, doing experiments, making observations, so they can figure out how stuff happens. And that's all pretty straightforward. The part that I think escapes notice is actually one of the most important parts, and that's the idea that scientists make predictions, right? That's where the real power is. Explaining means you're looking at something and you're saying this happens because. Predicting means you're going to look ahead at the future and say, under these conditions, this will happen. And that's super important as we look ahead. Engineers, biologists, everybody. So that's the idea of what we're looking at in this video. And I want to start off by saying, like, why does stuff happen? How will it all end up? And the short answer is it's all going to end up at equilibrium. Changes take place, right? And we can witness changes as things that are happening. We can figure out why it's happening. We can look at what will happen. We can look at how long it will take to get there. And all of those things are based on the idea that we have these changes, right? And things need to end up a certain way, or things will end up a certain way. And that way is a balanced way. And that balanced way we describe as being in equilibrium. So that's the first idea I want to mention here, is there's this thing called equilibrium that we talk about. And that's how everything's going to end up. That's the short of it. Like, how are things going to end up? They're going to end up at equilibrium, right? Batteries don't die. They reach equilibrium. So what is equilibrium? Well, equilibrium, from a chemistry standpoint, is a state in which there is balance between reactants and products. And I think that's a reasonable idea, and we can look at it, step back a bit and say, you picture chemical reactions as going from reactants to products, and that's it, right? But in reality, you have reactants going to products and products turning back into reactants. It's a tug of war back and forth between reactants and products, and it isn't always a one-sided battle. So that's a very, very important idea. And then the other important idea there is that the reactions generally don't stop, all right? It's a tug of war that just keeps on going and keeps on going and keeps on going. So the idea is things reach a steady state, a state of balance, and there's no net change, even though there's, you know, atomic level changes all the time. And if we can step one bit further into the chemistry version of equilibrium, we're talking about reaction rates, how quickly things are happening. So we talk about forward reactions and we talk about reverse reactions, which is not something that you've probably discussed before in chemistry, but reactions don't just go one way. Just like a tug of war generally doesn't just go one way. So reaction rates, that's going to be the basis of how we find out we're at equilibrium, or how we see we're at equilibrium. So let's take a step back and look at the idea of equilibrium in some intuitive way. I have a spring here, and we can so we'll just declare that spring's at equilibrium. It's just sitting there, right? And there's all kinds of ways it isn't, but we're going to ignore those. So anyway, if I take this spring and compress it, right, I have some observation. The spring is shortened in distance. I've done some work on the system, right? F equals kx or whatever, and W equals FD, right? All kinds of exciting things. And I can predict what will happen. I have compressed it, I've decreased its length, and if I let go of it, its length will increase. So there's my prediction, and it would be even more powerful if we could predict how it was going to end up, right? So as I let go of it, it's going to increase, and it happens to get that long, okay? And so I can make a different change, an alternate change on the system, and I can stretch the spring. And then when I let go, I can predict it will get smaller, and it's going to end up, it turns out, at that same length as it did when I compressed it. And that length we will declare as our equilibrium length for that spring. No matter what I do to it, it's going to end up back in that equilibrium state. Anything other than that is a higher energy state. So that is our equilibrium state for the spring. And that's probably a little more intuitive at first than the idea of equilibrium for chemical reactions. So I have an analogy that I use for my students very often, and it involves an amusement park on an island with just one road leading in and out. I guess it's like the plot for a horror movie, but so is my class. All right, so this is a parking lot, and I think that's a hugely important part of any amusement park, since most people spend the most of their time there. And we're going to say that this parking lot is reached via a bridge, and that bridge is a 2-lane road. And I'm going to draw in, we've got these parking spaces, right? Angle parking for you engineers out there. Far less painful for me than straight parking, but whatever. So we've got cars lined up here at the start of the day, and there's no cars in the parking lot, all right? So that's the beginning of the day, and our cars outside of this are our reactants, right? The things we start with in a chemical reaction, and our things in the parking lot we're going to declare are our products. So in a typical chemical reaction scenario, we're going to start with all reactants, and we're going to start with no products, right? And then we're going to do whatever to start this reaction, kick in some energy. The gate's going to go up, and the first car is going to go into the parking lot. And at that point in time, the part that isn't intuitive about chemical reactions is, as soon as the car goes in the parking lot, as soon as we have made some products, there's a certain probability that that's going to turn right back into reactants. But if I have small children, so this particular scenario makes a lot of sense to me, which is we've been sitting in line for a long time. My children have been beating on each other and screaming for an hour. Look, boys, if you don't knock that off, I'm going to turn this car around. And then, they call that bluff, and I turn the car around. So as soon as you have a product, there's a chance that it's going to go back to becoming a reactant, and maybe I change my mind and hop back in line, and then that just continues, all right? Anyway, these things, this can go back and forth. Now, in the beginning, the rate going in is very, very, very high because that's where everyone wants to go, but there's still a couple cars trickling out. As time goes on, the rate of cars going in slows down and slows down as this parking lot starts to fill up. We get more and more more and more products in this case. And eventually, all of these parking spaces are going to be full. And at that point, no longer can cars enter the parking lot, well, theoretically, until cars start leaving the parking lot. And this is a very important situation because cars will enter the parking lot only as quickly as cars are leaving the parking lot. So our rate of cars entering the parking lot is exactly equal to our rate of cars leaving the parking lot. Our rate of products forming is exactly equal to our rate of reactants forming. And that is the state of equilibrium, right? The rates are the same. And overall, if we were counting cars, we wouldn't have a net difference, a change in that side. So I had said earlier that our equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. I think this is a fairly intuitive way at seeing how that works. Okay, so that's the basic idea of equilibrium. And knowing that, we have to answer the next question, which is, why does stuff happen at all, right? And I'm going to take this page away, and I'm sure I will refer to it again in a bit. And the idea of why do things happen at all is based on balance, all right? And I think that's a rather intuitive idea. A balanced state is more stable, it's more favorable. And like if you were to spin a top and ignoring all the drag and frictional loss and all that, it'll wobble, wobble, wobble until it hits that balance point, and then it just spins perfectly in place. That's an equilibrium state for that, right? And balance is the natural state. That's how things should be. It's going to wobble back and forth until it reaches that. So the question is, why do things end up at equilibrium? And those things end up at equilibrium, this balanced state, because it's a low energy state, right? It's more probable if we look at it in terms of maybe entropy or positional probability. So those are general terms. Let's look at the chemistry terms for this. And those chemistry terms involve the entropy of the universe, all right? And it doesn't really matter if you know those words. The second law of thermodynamics states that the entropy of the universe must be positive for any change to take place, right? What does that mean? That means the universe is getting more and more disordered over time. Something won't happen unless it makes the universe increase in disorder, all right? It turns out measuring the delta S of the universe, the entropy of the universe, is kind of difficult, but Josiah Gibbs made up this thing called Gibbs free energy, and that's a way that we can utilize things like entropy, disorder, and enthalpy, heat content, and figure out an energy difference between reactants and products. And that's why things happen, is there's some difference in energy between reactants and products. And we measure that in terms of a Gibbs free energy. All right? So that is the idea of why things happen to reach a lower energy state in as few words as possible. So then we need to be able to describe, like, what does that equilibrium state, that low energy state, look like, right? And the good news is we can describe it. And we describe it by looking at our reactants and our products, right? The things that we start with and the things that we end up with. And we see how much of each there is at equilibrium. And their difference in energy determines what we call an equilibrium constant, K. And we'll see that K is a special type of Q in a moment, if you like letters. But the idea is, at equilibrium, we're describing this picture of how things are going to be at equilibrium by looking at how much reactant we have and how much product we have formed once things are at equilibrium. And again, I don't think it's intuitive to say not every reactant has turned into product, but that is the case, right? It is not necessarily a completely one-sided tug of war between reactants and products. The balanced low energy state may be somewhere in between them. So that is the idea. We describe how equilibrium will look by looking at an equilibrium constant, a ratio. And that ratio is a special type of reaction quotient, all right, based on Vogt and Goldberg's law of mass action. It doesn't matter, but we need to be able to describe how things look now so we can compare it to how things will look eventually and predict how changes are going to take place, right? So K is where things are going to end up, and we have this thing Q, which is how things are right now, okay? K, how things are. Q, how things are. K, how things are as things end up. Q, how things are at any point in time. So when we compare them, we can predict how changes are going to take place. Are we going to make more product? Are we going to make more reactant? Or are things going to stay in a steady state? Are they already at equilibrium? And I do want to mention Q and K. Ks are a type of Q. All right. A reaction quotient describes a ratio of products to reactants at any point in time. K is a special type of reaction quotient that describes the ratio of products to reactants when things are at equilibrium. All right? So all Ks are a type of Q. Not all Qs are a type of K. K is a special Q. And the math analogy would be that, like, Q is like a rectangle, K is like a square. All squares are rectangles, but not all rectangles are squares. So this is our power. Delta G is telling us why things are going to happen, and comparing Q and K is going to tell us how things are going to happen, and Q is going to tell us how things end up when it's all said and done. Which brings us to how quickly things are going to take place. And it would be nice if, when we have changes taking place, we could work in the duration of that change and how it gets from reactants to products. So I have a piece of paper here. And we're going to look at a scenario that seems pretty reasonable, which is I have a piece of paper, I have this lighter, and I'm going to light the piece of paper on fire. No surprise that it burns, all right? So we can make an observation here. Our observation might be it's burning. It's giving off light, it's giving off heat. We might explain it, right? We could explain it as something as simple as, like, I lit it on fire, right? Or we could say, you know, the oxidation of carbons and hydrogens is exothermic, and that's giving off the heat as they reach the lower energy state of the carbon dioxide and the water vapor, yeah? So there it is. And we can predict, you know, maybe if I light other paper or other things on fire, we'll get an exothermic oxidation like that. That happens to be a rapid one. So that's a simple idea of kinetics, how long things take. So our Gibbs free energy, our delta G, tells us things happen to reach a lower energy state. Delta G will tell us whether or not something will happen, okay, or is likely to happen. And kinetics will tell us how long it's going to take. And I don't think that's super intuitive to separate those things. When we first teach Gibbs free energy, it's like, that has a certain value, that will happen. Yes, but maybe it'll take a bajillion years to happen. And so we have to work kinetics in. And I think a simple example of that, or an extension of our predictions, I have this bolt right here, and it's made out of iron. If I leave a bolt out in air, it will eventually rust, especially moist air speeds things up, kinetics. But I can try and light this bolt on fire the same way I did the piece of paper. Maybe oxidation of this bolt is an exothermic process, like oxidation of the components in that paper are an exothermic process. In fact, it is, right? So if I heat this bolt up, try and give it enough of an oxidation energy to kickstart the reaction, it's oxidizing, right? And it happens to be an exothermic oxidation. It's giving off heat, but you can't tell because it's really slow, okay? And I think there's no surprise that my bolt did not start on fire there. In the same note, though, we could have had an analogous situation where I had a piece of paper that I tried to light on fire. And yes, it's burning. We can all agree, but it's burning much slower, right? So yes, paper burns, right? There must be some factor that affects how quickly it burns. Just like, yes, iron will oxidize, and there must be some factors that determine how quickly it will oxidize. And for a comparison, I have some steel wool here. There we go. I have some steel wool here, and that's just fine strands of iron. And if I put a flame to this, unlike our steel bolt, we are going to get it burning, right? So that brings our third factor into play here, which is delta G telling us things will or won't happen, or at least will or won't happen in a certain direction, and kinetics telling us how long it's going to take, right? And that's for a specific change. So the overall idea there, we have a different K, and that's somewhat problematic, and I understand capital K is an equilibrium constant, and lowercase k is a kinetic rate constant. So let's just push this aside. With our capital K, we're talking about about equilibrium, right? And with our lowercase k, we're talking about kinetics. And that's just how it is. I have no control over the fact that that's a little confusing. And one of the questions we'll answer in a different video is, are K and K, uppercase K and lowercase k, related? The short answer is no, but there's fine print that kind of makes the answer yes sometimes. But we'll just say no. If anyone ever asks you, big K and little k, not related. All right, so let's summarize what we've seen here, and then we'll plan ahead for some future videos that go along with this. What are we looking at, right? Why does stuff happen, and how's it going to end up? All right, and how will it end up? And this how will it end up is the idea of equilibrium. Okay, that is how things are going to end up. And our delta G, our Gibbs free energy change, is going to be based on our delta S of the universe. And that tells us why things change. This energy balance gives us some driving force. The capital K value that we have tells us how things will look at equilibrium. So this gives us how things will look at equilibrium. Q tells us how things look at any point in time. Right, we'd say now. How do things look right now? That's what Q is. Is it possible that things look right now the way they will look at equilibrium? Yes, K is a version of Q. It's a special case of Q. And then we had our kinetics, right, with a lowercase k. And lowercase k is going to tell us how long it takes. And it turns out how we get there. So how long it takes / how to get there. And that's a subtle distinction between how things are going to change and how they make that change, all right? How they get from reactants to products. And that's a fundamental difference between kinetics and thermodynamics. So how's it all going to end up? Equilibrium. That's the short answer.